Hi everyone, this is the second in a series of 2 videos covering the topic of mathematical induction for Extension 1 Mathematics for the New South Wales curriculum. So in this series of videos we've looked at what is mathematical proof and then proof by mathematical induction, and we've looked at 2 types, summation and divisibility. This video is going to cover the divisibility type of mathematical induction, and then we're also going to look at when mathematical induction doesn't work. Recall that the process of mathematical induction is as follows. We have to show that the statement is true for n equals 1 or some initial or base value. We have to then assume that it's true for n equals k, some arbitrary value, and then prove that it's true for the next value after k, or n equals k plus 1. And here's our conclusion: since it is true for n equals 1 and proven true for n equals 1 plus 1 equals 2 and so on, therefore it is true for all n. So let's look at our first example of a divisibility type. Prove that 5 to the power of n plus 3 is divisible by 4 for all positive integers n. Okay, we're going to go through the process. Step 1, show that it's true for n equals 1. So this is just a matter of substituting in 1 for n here, which gives us 8, which is divisible by 4. So it's true for n equals 1. Step 2, assume it's true for n equals k. Now we can substitute the k in here, but that's not going to show that it's divisible by 4. So we're going to make it equal to 4 lots of some letter. I usually use capital M, but you can use whatever you like. And then we must state where m is an integer. So this is stating that this expression is divisible by 4 because m is a whole number. Step 3, prove that it's true for n equals k plus 1. So we're going to start off by substituting in k plus 1 where the n is. Now we're not going to use the method that we used for the summation type, where we go sum of k plus 1 terms equals sum of k terms plus the k plus 1th term. It won't work in this situation. What we're going to do is try and substitute this in our assumption from the previous step into here. So I'm going to split this up into 5 to the k multiplied by 5. And now instead of the 5 to the k, I'm going to write 4m take 3. Don't forget your brackets. Expanding that out gives me 20m take away 15 plus 3. Tidying it up, I get 20m take away 12, which I can factorize a 4 out. And it's because I've got 4 multiplied by an integer, then it's divisible by 4. So we've actually finished. Therefore it's true for n equals k plus 1. Therefore it's true for all n. Let's try another one. Prove that n cubed take away n is divisible by 3 for all integers n greater than or equal to 2. Now this one is subtly different than the other ones that I've shown you in that it starts at 2. It doesn't start at 1. It's obviously not true for 1. I put 1 in there, and in there I get 1 take 1, which is 0, which is not divisible by 3. But that's okay, we're just going to start at 2. So our first step is going to be to show that it's true for n equals 2. Substitute your 2 in, we get 8 take away 2, which is 6, which is divisible by 3, so it's true for n equals 2. Step 2, assume it's true for n equals k. Substitute the k in. We're going to write k cubed take away k is equal to 3 lots of some integer. Step 3, prove that it's true for n equals k plus 1. Now let's substitute our k plus 1 in here. We're going to have to do a bit of expansion here, but that's all right. I'm looking up here to see what I can do. I think I'm going to expand this all out, and then instead of the k cubed, I'm going to substitute in 3m plus k. Okay, recall that k plus 1 cubed is k cubed plus 3k squared plus 3k plus 1. And then I've got take away k, take away 1. All right, tidying that up, I'm going to get k cubed plus 3k squared plus 2k. Instead of k cubed, I'm going to write 3m plus k. And when I sort that all out, I get 3m plus 3k squared plus 3k, which is divisible by 3. Therefore, it's true for n equals k plus 1. Therefore, it's true for all n. Here's a third example. Prove by induction that 47 to the power of n plus 53 lots of 147 to the power of n minus 1 is divisible by 100 for all integers n greater than or equal to 1. This one looks a lot harder, but it's not too bad. There is a bit of a trick to it. But let's start the same way. Let's show that it's true for n equals 1. So it's going to be 47 to the power of 1, which is 47, plus 53 lots of 147 to the power of 0. This, of course, is equal to 1. So 47 and 53 is 100, which is divisible by 100. Therefore, it's true for n equals 1. Step 2, assume it's true for n equals k. Substitute in for k and put it equal to 100m, where m is an integer. Step 3, prove true for n equals k plus 1. So we'll begin by substituting the k plus 1 in where the n's are. 47 to the power of k plus 1 plus 53 times 147 to the k. Now don't be tempted to multiply these two together, because this is to the power of k and this isn't. So this is 53 times 147 times 147 times 147 k times. So just leave that alone. Have a look up here and see how we might substitute this in to this expression. I'm going to use the 47 to the power of k, so I need to make that out of this term. So that's 47 times 47 to the k. So instead of 47 to the k, I'm going to substitute in 100m, take 53 times 147 to the k minus 1. And we'll put it in brackets. Now we're going to expand that out. 47 times 100m is 4,700. Take away 47 times 53. It's fine to multiply those two together. 2,491 times 147 to the k minus 1, and that's the same term there. We're nearly there. We need to try and factorize this and get it together. So it's got a common factor of 147 to the k minus 1. Have a look. This is the hardest part of this question. 4,700m. Take away. I've brought out the 147 to the k minus 1 at the front. Brackets. It's multiplied by 2,491. This is going to become a minus because I've taken the minus out the front. 53 lots of 147, because 147 to the k minus 1 times 147 is 147 to the k. All right, so just check that and make sure that makes sense to you. Now, putting that in the calculator, we get 5,300, which is a multiple of 100. And so this is divisible by 100. Therefore, it's true for n equals k plus 1. Therefore, it's true for all n. All right, last example. Prove by induction that n cubed plus n plus 1 all cubed plus n plus 2 all cubed is divisible by 9 for n equals 1, 2, 3, etc. Okay, same process. Step 1, show that it's true for n equals 1. So we're just going to substitute the 1 in here where the n's are, and hopefully we'll get a multiple of 9. 1 cubed plus 2 cubed plus 3 cubed is 36, which is divisible by 9. Therefore, it's true for n equals 1. Step 2, assume it's true for n equals k. Let's just substitute the k in, and we're going to put it equal to 9m, where m is an integer. Step 3, prove true for n equals k plus 1. Okay, so let's substitute that in here. Gives us k plus 1 all cubed plus k plus 2 all cubed plus k plus 3 all cubed. Now, don't immediately go on an expanding frenzy, because that will be a lot of work that will be wasted. Let's have a look up here at what we're going to try and substitute in. So we can't substitute for the k cubed, but we could for k plus 1 cubed or k plus 2 all cubed. And I've decided to do the k plus 2 all cubed. So instead of this term here, I'm going to put in 9m, take k cubed, take k plus 1 all cubed. Have a look what happens. These two are going to cancel out, and I've substituted for that one, so the only one that I need to expand is this k plus 3 all cubed. Okay, let's tidy it up. So I've got 9m, take k cubed, these two cancel, and then expanding this I get k cubed plus 9k squared plus 27k plus 27. Okay, we can cancel these two out, and I can factorize out a 9, which shows that it is divisible by 9, and so we've proven it true for n equals k plus 1, therefore it's true for all n. Okay, we're going to finish off this topic by looking at when induction doesn't work. Now, with proofs, a single counterexample is sufficient to disprove a result. Let's look at this statement. The sum of two composite numbers is a composite number. Well, do you think that's true? Let's have a look at it. 2 plus 4 equals 6. 2 and 4 are both composite. 6 is composite. Yep, it's true for those numbers. 6 plus 9 equals 15. 6 and 9 are both composite. They add to 15, which is composite as well. But look at this one. 8 plus 9 equals 17. 8 and 9 are composite. 17 is prime. So can you see what I'm talking about? We have a single counterexample which has disproved this statement. Sort of the same with mathematical induction. It's not sufficient just to do steps 2 and 3. That's where we assume that it's true for k and then prove it's true for k plus 1. We have to show that there's an initial case or a base case that's true in order for induction to work. We've got to have something to build upon. Let's look at this example. Show that n squared plus n plus 1 is even for all n. So let's start at step 2. Assume it's true for n equals k. It means that k squared plus k plus 1 is an even number. Now prove it true for n equals k plus 1. Substitute our k plus 1 in here. So we get k plus 1 all squared plus k plus 1 plus 1. Expanding out those brackets, I get k squared plus 2k plus 1 plus k plus 1 plus 1. Now we know that this bit here is even. Okay, so k squared plus one of those plus that is going to be even. So I'm going to take this k out and join it with that one. Have a look. K squared plus k plus 1 plus 2k plus 2. Now that's even. Okay, that's from our assumption here. And this is even because it's 2 lots of k plus 1. So this is an even number. So it looks like we've proved it. There's just one thing wrong with this. It's not true at all. Put in, say, 1. 1 plus 1 plus 1 is 3. It's not even, it's odd. Do you see? So we don't have a base case to build upon. We've proved that if we've made this bogus assumption, then we can prove that the next one is true. But this is not correct. There are also instances where we can't use induction or when it's too difficult to use it. Here's some examples. Prove that if a 3-digit number is divisible by 3, then the sum of its digits is divisible by 3. So this one doesn't really fit the induction method. We'd have to assume that it's true for a particular 3-digit number, an arbitrary number, and then prove it true for that number plus 3, because that would be the next number that would be divisible by 3. And there's a much easier way to do this particular proof. Here's another one. Prove that 2 to the power of n take away 1 is prime for all prime numbers n. And the problem with this one is that we don't know the sequence of prime numbers. If it was odd numbers, it'd be all right. We could prove it true for k and then k plus 2. That would give us the odd numbers. But with prime numbers, we could assume this is true for k. We don't know what the next prime number is after k. Okay, that brings us to the end of the topic for Extension 1 Mathematics. If you want to know more about proof or you want to study the Extension 2 topic, then you can go to the link at the top of the page.